54. Carbon tetrachloride, an important industrial solvent, is prepared by the chlorination of methane at 850 degrees Kelvin. And then they give us this balanced equation. So we have methane, which is CH4 gas, plus 4 Cl2 gas, and that gets converted into carbon tetrachloride, CCl4 gas, plus 4 HCl gas. What is the equilibrium constant for the reaction at 850 Kelvin? Would the reaction vessel need to be heated or cooled to keep the temperature of the reaction constant? Okie dokie. So, let's see. They're asking for the equilibrium constant. An equilibrium constant is a K value. So we're trying to solve a K value at a certain temperature. Now, it doesn't really matter what K we're solving for here, right? Whether it's Ka, Kb, Kc, Kd, right? I could probably assume that it's going to be a Kp because they're all gases and gases have pressures to them. But it doesn't really matter because there's only one formula that links a temperature with a equilibrium constant, and that's this formula down here. So let's just put this over here. I guess we'll put it down here. Maybe over here. That looks good. So K equals the E button on the calculator raised to the negative delta G divided by R times T. Now, we want to solve for that equilibrium constant, which means that we should know the Gibbs free energy, the R value, and the temperature. So let's start with the R value. That's always going to be a constant. That's 8.314. Always 8.314 if we're using energy values, aka joules. The units for the R value is joules per mole times Kelvin. So delta G is only allowed to be in joules, and the temperature is only allowed to be in Kelvin. But that's good, because they gave it to us for 850. So I don't have to convert here. They already told me 850 Kelvin. So I have the R, I have the T, the E button is on the calculator. The only thing that's left is if I want to find that equilibrium constant, I have to find the delta G. So some of you might say, okay, I'll just go in the back of the textbook to find out all the delta G values for each individual component, products minus reactants, and solve. However, we can only use the delta G values in the back of a textbook or an appendix value if you're at room temp. Room temp is 298 Kelvin, not 850 Kelvin. So there's got to be another way to get the exact Gibbs free energy at 850 Kelvin. So now I ask myself, well, what other formulas is there that link a delta G value with the temperature? And that's this formula down here. Delta G equals the change in the enthalpy minus the temperature times the change in the entropy, right? But now the thing is, well, I don't have an H value and I don't have an S. Those are fair game to go in the back of the textbook to find out the individual components. So that's exactly what I did. I went in the back of the textbook to find out all the delta H values and the delta S values for each individual component in this balanced equation. So now, let's work one at a time. Let's focus on, well, what is the overall delta H for this equation so that I could plug it into my formula? Well, the formula to find out a delta H for a whole reaction is this, right? It's delta H for the whole entire reaction. Rxn is reaction, is the sum. So this means sum plus, right? So we're going to add up all the products and minus the sum of all the reactants. So essentially it's products minus reactants. But you got to be careful because these values that are in the back of the textbook, they're only for one of your compound. So you just have to check. Well, in this case, I only have one CH4, so I times this by 1. But for the Cl2, I have 4 of them. So technically it's 0, but I would times it by 4, but 4 times 0 is 0. I only have one CCl4, so I'm going to times that by 1, but then I have 4 HCl's, so I have to times this by 4. Now you have to sum them up. It's literally CH4 plus Cl2, so I have to add these, but that would be the same number, right? Negative 74.6. Nothing really went on here. And then for CCl4 plus HCl, I have to add these together. So let's just plug it into Calci. Lovely, lovely Calci on the left-hand side. So I'm just going to say negative 95.7 plus 4 times negative 92.307. Okay, so the total here would be negative 464.928. And maybe I'll just drop these down a little bit. There you go. So now we have the sums for both the products and the reactants, so let's just add them together, or in this case, subtract, right? Products minus reactants. So negative 464.928 minus the reactants, which is a negative 74.6. So my delta H for my whole entire reaction would be this value. Love this calc because I could just go up and grab the whole value. Less room for error, minus a negative 74.6. And this is negative 390.328. And now I'm just going to have to bring this over a little bit. There we go. Units for your delta H, it was kilojoules per mole, but all these values were mole values, the coefficients. So the mole gets canceled, so you're just left with kilojoules. All right, so we got the delta H for the whole entire reaction. Now we just have to do the same thing for the S's. So I could use the same formula, which is this one, but instead of saying H's, I can erase all the H's and I could input S's. So the delta S for the whole entire reaction is the sum of the S products minus the sum of the S reactants. Same exact idea. I take the values that I found in the back of the textbook and I times them by their coefficients. So I have 1 for this, I have 4 for this, 1 and 4. And now I have to add the blues together, the reactants, I got to add the products together. Let's throw them on into the calculator just to see what's going on. 186.3, not times, plus 4 times 223.1. And that looks good to me. So I have a total of 1,078.7 for my reactant side, 309.7 plus 4 times 186.9. So I have a total of 1,057.3 for the product side. Products minus reactants, let's see what we get. So 1,057.3 minus 1,078.7. Delta S for the whole entire reaction is, I'm just going to grab the values in my calci minus this other number. I'm going to grab that. Beautiful. So we have a negative 21.4. Units here, the moles cancel because we multiplied by the coefficient, so it's joules per Kelvin. Okay. So we have the H value, we have the S value, we have that temperature, it was 850 Kelvin. Now we can use this formula to solve for delta G. So let's do just that. So delta G equals the H value, but wait a minute, this is in kilojoules and the delta S is in joules. You can only have one. Whether it's going to be in kilojoules, whether it's going to be in joules, which one are we going to convert? Well, remember, go back to the original question, right? If we want to put that delta G in here, the R value says, I need it in joules. So I'm going to convert the kilojoules into joules. And that's okay, right? Kilojoules to joules, you times by 1,000, or just take the decimal and move it to the right 3 spots. So this would be negative 390,328 now. 390,328 joules. And that's the number that's going on in here. So 390,328 minus the temperature, which was 850 Kelvin. And then I'm going to times it by the delta S value of a negative 21.4. And now delta G for the whole entire reaction would be negative 390,328 minus 850 times negative 21.4. And that looks good to me. Press enter. It's not the answer, so I'm not going to round. 372,138 joules. And that's the value that's going now over here. Negative 372,138 joules. Now I have everything to plug in into this equation. So K equals E raised to the negative fraction. The negative is in the formula. But then we have a delta G that's also negative. So that's going to become a positive. Right? 372,138, all divided by the two variables, right? The 8.314. And then the temperature, which is 850. Now, what I would do is I would just get this to being one number, right? So I'm just going to simplify that so that we just have K equals E raised to some number. Let's see. Negative times a negative divided by 8.314. And now if I want to just show the 850 in the denominator without any parentheses, I'll press divide again. Divide by 850. And I have E raised to 52.659 and a bunch of other numbers, which I'm not going to round, but I'm not going to write them all out. So let's just do it. Second ln. That's the E button. I'm going to grab the whole value in Calci, press equals, and there you go. 3 sig figs, I guess. So technically there's 2 here for 850. So maybe we'll only use 2. So 7.4. 7.4 times 10 to the 22nd. Very spontaneous. Very large K value. Your K values do not have any units, so it's just 7.4 times 10 to the 22nd, and that's the equilibrium constant. So what's the equilibrium constant? 7.4 times 10 to the 22nd. Now, would the reaction vessel needed to be heated or cooled to keep the temperature of the reaction constant? Now, we're talking about heating, right, or cooling. That has to deal with heat. So this is going based off of the delta H value. Now, for the delta H value that we found, this was negative, right? It was a negative 390 kilojoules. And a negative delta G means that we are exothermic. So always a negative delta G means that we are negative delta H means that we're exothermic. And that always means that we are losing heat, right? We're giving off heat. So you're giving off heat to the surroundings. So that means that the surroundings are going to start getting hot, right? So if you want to keep that temperature constant and you're giving off that heat, you kind of have to do the opposite. So if this reaction is giving off heat to the environment's starting to get hotter. So in order to keep the temperature constant, right, if the temperature is rising because it's getting hotter, we need to cool it down. So for exothermics, we need to cool it down. So it needs to be cooled. Because giving off heat is going to raise that temperature. So in order to bring it back down, you just got to cool it down. So that would be the answer to the second part. And there you go. Thank you for viewing this video. And I hope you learned from this video. Let me know in the comments. There's a lot going on here, but you guys got this. All right. Good luck on your future tests and quizzes, and I'll talk to you all later, all right? If you wouldn't mind, please press the subscribe button if you haven't subscribed already. We're almost at 25,000 subscribers, and that's all because of you guys. Thank you so much. Let's keep learning, and I'll talk to you soon. Bye-bye.